prepare yourself for the exam. I'm gonna post the new homework today. I mean, tonight or early this morning, tomorrow. So the due date will be Thursday, a week after the exam. So homework 4. Yeah, homework 3 is gonna do this Thursday, but I'm talking about the next homework, the new homework. No. Any question before we start? Today I'm gonna start solving a new example, and then we go through the chapter 3, and we start the harmonic excitation for 1 degree freedom system.
Question? Are we going to use some notes or a book or anything?
Yeah,
book.
Just the book?
Just
Yes. Let's look at this pulley system. You are asked to find the equation of motion and the natural frequency of this system. So there is one pulley here. All right, we have pulley 1 and pulley 2 connecting through this rope, and there's a mass connected to that, and one damper at the end of this system. So find equation of motion and natural frequency. So to do that, I would like to find the equivalent spring if I find the K equivalent for this system, then I can draw the free body diagram of this and derive the equation of motion and find the natural frequency. So to find the K equivalent, if the weight of this mass is W, if the weight of the mass on this side is W, so the force applied to the spring K2 is going to be 2W. So deflection I can say that central pulley 2 moves by 2W divided by K1, because we know that force would be K2 times deflection of the spring 2. K2 is now force is 2W, so 2W divided by K2 is going to be delta 2. Similarly for this one, so two forces applied here, W and W. So the force applied to spring 1 is going to be 2W down. So central pulley 1 moves by 2W divided by K1. This is what we know. And when you apply the force here, and when you push this one, this pulley is gonna moving down, and this pulley is moving up. So when you just apply the force here, this pulley is gonna move up. So moving down and moving up. Now, let's look at this problem in this way. If this is the motion of mass m, which are just showed by the x. If the central pulley is moving by this distance, by this amount, if this pulley just moving by this deflection is going to be that, the deflection, this rope is going to be 2 times of that. So if this is the true mass m moves by 2 times 2w divided by k2. So if you just move this by this deflection, the entire of the rope is going to move by 2 times of that. We have solved one problem like this before, so you know that. So if this guy is moving up, then the mass m is going to move by 2 times 2w divided by k1. So the total deflection is going to be 2 times 2w divided by k1 plus 2w divided by k2. So this is going to be the x, deflection of mass m. So k equivalent, I can write w is going to be k equivalent multiplied by the deflection of mass m, which is going to be x. So if I find x from here, x would be w divided by k equivalent. If I just equate this by w divided by k equivalent, I can cancel out this w, and I will get 1 over k equivalent equals to 4 over k1 plus 4 over k2. So k equivalent k1, k2, 4 times k1 plus k2. So equivalent k is going to be k1, k2 divided by 4 times k1 plus k2. So my original system just changed to the one simple mass and spring dampener. So if you want to write the free body diagram of this, the mass, the force is going to apply to that. It's going to be k times x. It's going to be c times x dot. So I can write m x double dot plus cx dot plus kx equals to 0. So this is going to be the equation of motion, and the omega n would be k equivalent divided by n, which is going to be this divided by So deriving the equation of motion, one problem at least is going to be on the exam how you can derive the equation of motion for a system which is given. So there are 2 methods, the energy method and free body diagram. So for second Newton's law. So by applying any one of these methods, we can find the equation of motion. Here, since we have the damping, we cannot use the energy method. So I just apply the other. Method to get the equivalent stiffness. Alright, any question on this? So in chapter 1 and 2, we just learned about the free vibration when there is no force applied to the system. And chapter 3, we will see the system which is under external force, and the external force is going to be harmonic. It's going to have the harmonic function. So we want to see how the system, how the response of the system can be determined. So chapter 3, the title is if we have a system like this, just simple mass and damping, it's under we have external force applied to this system. So the force is varying with time. So the force can be excited force can be harmonic function, or it can be non-harmonic. Or random. Random function like the earthquake. When you have the earthquake and it's vibrating, you have random function for the earthquake. For the harmonic function, suppose you have a pump or motor which is not balanced. So that imbalance is going to provide the harmonic exciting function to the system. So one example for that is going to be imbalance for example, pump or the blade of the blower is not balanced, so it's gonna make the harmonic function as an external force applied to the system. Or suppose the machine has been attached to the base, and the base of the machine has provides some motion. So motion so this is the machine which has been fixed to the base, but the base might have some motion, and this motion is going to provide the harmonic function. Now, in this chapter, we want to see what would be the response of the system if we have the harmonic excitation. So, if the Ft is a harmonic function, what would be the response of the system? Now, for that system, if I draw the free body diagram, I will see, I can have like something like this, free body diagram for this. This is mass M, force F applied at Kx, Cx dot, so Mx dot is gonna be negative Kx, this direction is gonna be negative. Negative Cx dot plus Ft, so I can write this Mx dot plus Cx dot plus Kx equals to F of t. So this is going to be the equation of motion for my distant places. Alright, any questions so far? We are going to find the solution of this differential equation. The solution of that is going to be the response of the system, because we are going to find x as a function of t, how x is going to change with time. So at the beginning of this course, you had an evaluation exam, and also in differential equation, we learned that if we have a non-homogeneous function like this, it's a second order differential equation which is not homogeneous because it has Ft. So the solution for this is going to be summation of solution of homogeneous part plus particular solution. So it's going to be particular solution. This is going to be the homogeneous solution. Homogeneous solution means if you solve this system, mx dot cx dot plus kx equals to 0. So the response of this, the solution for that, we call it homogeneous solution. The particular solution is the solution if corresponding to this force. So the summation of these two is going to give us the solution. If you have damping ratio zeta greater than 0, you remember that zeta is C over Cc. If it's greater than 0, it means if we have some damping on our system, then this part of solution, which is coming from this equation, is going to die when t goes to infinity. It dies when time goes to infinity. The vibration of the system for the homogeneous part is going to die. So as you are going to only have the particular solution. So this is one important thing. So for that reason, we call this particular solution a steady state solution, or a steady state vibration. So after a while, you are gonna have just the particular part of that solution. Now I will start looking at the system without damping. Then I will go to general. Okay. So undamped. Undamped system means C equals to 0. So the equation is going to change. Mx double dot kx equals to f of t. And since I mentioned that we are going to have the harmonic excitation, I assume that f of t is going to be f0 times cosine of omega t. f0 cosine of omega t is a harmonic function. So my function is going to change f0 cosine of omega t. Now, for the homogeneous part, mx double dot plus kx equals to 0. X of homogeneous is going to be C1 cosine of omega nt plus C2 sine of omega nt. For a system mass and a spring system, free vibration is going to have this response. We know about that. And omega n is the square root of k over n. K divided by n. This is the solution, homogeneous solution, which is corresponding solution. So, how can I find the particular solution? On differential equation, if you have a second order differential equation like this, to find a particular solution, you assume that your particular solution has a function very similar to your right-hand side function. So right-hand side function has a cosine function. I'm just writing cosine omega t with this amplitude. So how can I find this amplitude? I'm just plugging this in original function because this solution must be satisfied in this equation, and then I can find x. So m x double dot is going to be negative x omega squared cosine of omega t. So it's going to be m negative x omega squared cosine of omega t plus k times x cosine of omega t equals to f0 cosine of omega t. So I can cancel out cosine of omega t from both sides. I will get x times k minus m omega squared plus k equals to f0. So the amplitude of the particular solution can be found by this minus m omega squared plus k. Now I have the homogeneous solution, I have the particular solution. So x of t is going to be summation of these two. It's going to be C1 cosine of omega nt plus C2 sine of omega nt plus f0 dividing by k minus m omega squared cosine of omega t. This is going to be the response of this system if we don't have any damping. So it's going to be the homogeneous part. This is going to be particular part. Still we have C1 and C2 unknown. These are the coefficients. We should apply the boundary condition. So we know that, suppose we know that x0 is x naught and x dot 0 or v at time 0 is v naught. Just plug in 0 here. C1 cosine of 0 is going to be C1, C2 sine of 0 is going to be 0, F0 divided by K minus M omega squared times 1. So this must be equal to X naught. So X naught is going to be C1 plus F0 divided by K minus M omega squared. So C1 would be X naught minus F naught divided by K minus M omega squared.
Professor, how is the omega different from omega n?
So omega is the frequency of exciting force. It can be anything. Okay. Omega n is the natural frequency of the system. It's just a specification of the system.
Would be given then?
Omega n.
No, just omega.
Yeah, you know that which force is going to apply, which frequency is going to apply to your system. So if you know that, you would like to find the response of the system. What would be the response of the system? For x, how the x is varying with time. So omega and omega n would be known. Because for omega n, K and M are known, omega is the force applied to your system. This is how I can find C1. Similarly, I can find C2. You can, I'm not gonna show the process, but C2 would be this. So I can rewrite the X2 here. X2 is gonna be X0 minus F0 K minus M omega squared times cosine of omega nt plus C2 V naught divided by omega n sine of omega nt plus this part. Omega t. Make sure that you can see the difference between the terms. These two terms have omega n as a frequency, this one has the omega. So, is the general solution for the motion of undamped system, which is under harmonic excitation. Alright, here I could find the amplitude of the particular solution. I would like to just consider this x, so it's an important thing. So x is going to be F0 divided by K minus M omega squared. If I divide both sides by K, I will get F naught dividing by K, 1 minus M dividing by K, omega squared. Omega n squared would be K dividing by M. Omega n squared is going to be K dividing by M. So it's going to change to F0 dividing by K, 1 minus omega over omega n squared. Alright, this is the system that I have. It's under external excitation with the harmonic function. Now, if I just have a simple constant force, just simple F naught is applied to that. If I ask you what would be the deflection on that, you can say F naught would be K times delta, I just call it a static deflection. then the delta is gonna be F naught divided by K. So if you apply force M, just simple value of the F naught, if this is K, how much would be the static deflection F naught divided by K? Here I have F naught divided by K, so I'm just writing the delta static divided by 1 minus omega divided by omega n squared. Now x is, if you look at this, x is going to be the dynamic amplitude, delta static is going to be a static amplitude or a static deflection. So if I just divide both sides by this, I will get x divided by delta static is going to be 1 minus omega over omega n squared. This x is the dynamic amplitude. This is going to be the static amplitude. So the ratio of the dynamic to the static amplitude is going to be this. And we call this factor either amplification factor or amplitude ratio. Amplitude ratio or amplification factor. With sometimes, yeah, let's stick with that amplification factor. The ratio of omega over omega n, we call it R. So I can write x over delta static is going to be 1 minus R squared. One over 1 minus 1 R squared. Now, if I have y-axis as a function of x over delta static and x-axis as a r, omega over omega n. If I ask you to plot this is suppose y, this is x, function of y with respect to x. If this is 1, it's gonna be something like this. At r equals to 0, if you just plug in r equals to 0, 1 dividing by 1 minus 0, you will get y, or this ratio equals to 1. By increasing the r from 0, this guy is going to increase until you will get a value very close to 1. So it's going to be 1 minus 1, 0. You're going to get positive infinite value. So you're going to have this part. If r is passing 1, so r squared is going to be greater than 1, so this part is going to be negative. So you are going to have something like this. So this is a very important chart. I will talk about that very shortly. Any questions so far?
Either. Persevere. Yeah, what are we doing different? So, how does it know that we have off? How do you not know that shit? Yeah, that's what we do. We do. That too. What is super great? You can use this thing on the problem.
All right, three cases may arise. First case, case 1. When R is between 0 and 1, the frequency ratio is between 0 and 1.
Yeah, you have no problem.
He was.
So the excitation force had a form of harmonic function with cosine. We just assume that f equals to f naught cosine of omega t. The particular solution, if we just look at the particular solution, is going to be the capital X, which is going to be amplitude of the particular solution times cosine of omega t. So if R is between 0 and 1, this guy is going to be positive. So this guy is going to be positive. So 1 positive here times cosine of omega t. The external force was F0 cosine of omega t. So these two functions are in phase. So they don't have any different phase. So you can see they are moving with each other. The amplitude might be different, which is different, but we don't have any different phase. So I can say XP in phase with
Come out of the
the external excitation. So case 2, when R is greater than 1. When R is greater than 1, F0 is not going to change. This guy is not going to change. But this X is going to get the negative value because R is greater than 1, so 1 divided by negative 1. This one is always positive, so X is going to be negative. So 1 negative times cosine. So if you compare this to this one, X cosine of omega t plus 180. So XP in alpha phase by 180 degrees. So these two functions they are out of phase by 180 degrees.
she's like, oh, well, that just goes to show that you don't show me. That's the other thing.
Any questions so far?
No.
Because I just want to get the look at the first line of the last board. I just have the general solution for this case. I'm just rewriting again. The response of this system is going to be
No, I put like a building. You get to a point where sometimes someone's kind of like, oh, fuck this, maybe I'm like, that's fine, but that's off, because you try to say this, you see, like 60 out of 100, I'm not like, dude, just give me fucking 100, are you kidding me? I have to work.
Yeah, but now you're really mad just because you don't really good.
Yeah.
I don't know why you're getting so bad of shape about it.
You're
You're fucking rich about it.
Yeah. No, he would drop from that.
Did?
Yeah, he's like, come on.
alright. If I rewrite this again, I can write x0 cosine of omega nt plus b naught omega n.
You know, participation.
No, I'm not doing this. I'm like, dude, like, what the fuck?
Sine of omega
I
nt
just think I'm
plus
really like, yo, I'll break all planes because
this,
you transfer me.
this minus this. So it's gonna be cosine of omega t minus cosine of omega nt multiplied by f0 k minus m omega.
If you took magna, Lee would not know fucking Willis real quick. What the bank on the water? Sit there forever and be like, what's going on?
Now we can look at the case 3. Case 3,
I would skip that one.
when R is going 1 or omega over omega n is 1 or the natural frequency of the excitation force is going to be equal to the frequency of the natural frequency.
Oh, Michael step by step. Yeah, see, they
So now look at this part. If omega is very close to omega n, this part is going to be cosine of omega n minus cosine of omega n is going to be 0. This part, k minus m omega, if omega is equals to omega n, then it's going to be s square root of k over m. So omega s square is going to be k over m.
Just slacking.
So you can cancel out m and k minus k is going to be 0. 0 by 0. So we should apply the orbital law to find the limit of that. So I can get the limit of what would be this limit when omega is closing to omega n? Since this part is 0, this part is 0, 0 divided by 0 is not going to be defined. So I need to apply the orbital law. So I should differentiate both sides with respect to omega. So if I differentiate this with respect to omega, I will get negative t sine of omega t. If I differentiate this with respect to omega, coefficient of omega is here, I just put it outside, multiplied by f0. And this part, I will get minus 2m omega. So let me rewrite this again. I can cancel out this to negative. I will get t divided by 2m times m0 multiplied by sine of omega t divided by omega. So what would be the limit when omega is close to omega n?
Well, how many credits do you need? 60?
It's gonna be T times F0 divided by 2m omega n sine of omega n t. So this is gonna be the limit of that. So, omega n is omega n is the s square root of k over m. So this is gonna be t times f0 m s square root of k divided by m.
Some kids nothing to use class, and I just took credit. But then we're also fucking with those 12 business classes, and that's 4 credit classes.
Yeah, you could take all again.
Exactly, I got all my humanities out of it.
You still can.
Huh?
Yeah, you still can.
What?
If they take this lot.
Dude, I don't know.
If I divide both sides by k, just look at this. F naught divided by k, m divided by k, multiplied by s square root of k over m. So f divided by k is going to be the static deflection. M over k multiplied by s square root of k over m is going to be s square root of m over k. S square root of m over k is going to be 1 over omega n. So omega n comes up, so I will get T times static deflection times omega n divided by 2 multiplied by sine of omega n.
And I can show
Now I can rewrite case 3 by this. X c is gonna be x naught cosine of omega n t plus x naught divided by omega n sine of omega n t, just the first two terms, v naught. And the last term is going to be there. T times delta static times omega n divided by 2 sine of omega n t.
When you said that, I thought you really was like, hey,
This is going to be the solution, the response of my system when omega over omega n is 1. Now, if I want to draw the x as a function of t, it's going to be like this function, this graph. So you see how the particular, I'm just plotting this part. If I just plot the particular solution, which is xt, we can see it has a t here. So the x is increasing when time is increasing. So you can see when time is passing, you are gonna have a huge amplitude on the particular part. So if I just connect these peaks, the equation of this line is going to be like this. X would be 3 times delta static this is the equation of this line. If you just connect the peaks. The sine of omega n is gonna repeat itself. It's a period of oscillation, 2 pi divided by omega n. This part is making the harmonic solution. Harmonic part, you can see it's repeating itself after 2 pi divided by omega n, but it's increasing. So maybe after, it depends on the system, 10-15 seconds you are gonna have a huge amplitude and your system is gonna fail. So you are gonna have failure on your system. Look at this system that we have here. It's a simple mass and a spring. Suppose the frequency of this system, the natural frequency of this system is 1 Hertz. The natural frequency of this system is 1 Hertz. So if you apply the external force with the omega of 0.4 Hertz, you apply a force by the frequency of the 0.4 Hertz. Omega is 0.4 Hertz. You can see how it's oscillating. The response of the system can be obtained by something like this. Or if it's 1.6, you are get the response easily. But when the frequency is very close to the natural frequency, you can see how would be the motion of this mass is changing. So you are going to get a huge deflection on the system. And if it's 1, this guy is going to go to infinite and you are going to have a failure. So it's very dangerous for a system if it's on the excitation force with the frequency very close to the natural frequency of the system. Something like this. So if you have a system in which you have the external harmonic function, if the frequency of that is very close to this, it's going to be dangerous for the system. You are going to have failure. So one important as a mechanical engineer, if you want to design a system, you should avoid this case. So to avoid this case, first of all, you need to find the natural frequency of that system. Then you should avoid to have excitation force to the frequency very close to the natural frequency of the system. So this is how it works. Any question? Let me solve one example.
Somebody said it was like $80. Oh, yeah, no,
It's like 60.
Suppose there is a beam which has been fixed from both sides. The length of the beam is 100 inch. This is the cross section of the beam, So the cross section is 0.5 inch and distance is 20 inch. So 0.5 and 20. So there is a pump here, just at the middle of
Well, ours are colored too. Oh, like you guys might like that color. It's like the color scheme that goes on the fridge for that's okay. Yeah. Huh? Mm-mm. We go. Yeah. I don't know if that's
So there is a pump here, it's rotating, so it's just showing a pump mounted at the middle of this thing. So due to unbalance on the pump, this pump is gonna apply a force with the magnitude F equals to 50 times cosine of 60.83 times t. So one force with this amplitude and this angular velocity or frequency has been applied to the middle of the beam. We would like to get we would like to know how would be the deflection of the beam. So when one force with this magnitude and this frequency applied to the middle of the beam, how would be the deflection of this beam is right. So if you look at the first page of your textbook or yours on the back of the machine design book, you will figure out that why the deflection. If you apply a force, you are going to have deflection. How the y is varying? The y is going to be force times n power 3 dividing by 192 ER. So if I just write it down in this form, force would be 192 times EI dividing by n power 3 times y. Now you could connect the deflection to the force. So this coefficient is going to call K equivalent. So K equivalent for this system is going to be 192 AI dividing by N 3. And I forgot to mention that the mass of this is 150 pound force. This is the weight. I should change it to the mass. So the mass of the pump is 150 pound force. So then I'm just changing this system to simple mass and a spring, something like this. So mass, the weight is 150 pounds. I can change it to the mass. 150 dividing by 386.4 is gonna give me the mass 0.388. This is the weight. I have to change it to the mass. So this is the conversion to change the mass pound to the mass weight pound to the mass pound. So this is the mass. I have a K, I can calculate K, then I can find the response of this system. To find that, I need to get first the value for the K. EI divided by L power 3. The modular elasticity is 30 times 10 power 6 psi. I would be VH power 3 divided by 12 out. So it's going to be V is 20, H is 0.5, power 3 divided by 12 is going to be 0.208, and L is 100. 192 times 30 power 6 times 0.208 divided by 100. I will get 1,200 pounds per inch. This is my string constant of the beam. Now I'm gonna find the value for the x. The value of the x, if you remember, it was f0 divided by k minus m omega squared. The force applied to that is 50, the amplitude of that is 50. 1200 minus 0.388 times omega squared. Omega is 62. If I get that, I will get negative 0.1504. So the response, the particular response of the system is going to be negative 0.1504 multiplied by cosine of 62.8 times t. This is how my beam is vibrating. So the amplitude, the frequency is going to be the same as the frequency of the excitation force. And I just wrote the particulars part. I didn't write the homogeneous part. The homogeneous part is not difficult to find. And x double dot plus kx equals to 0. So the response of that. Now, you see, since I got the amplitude negative, it means I have on case 2 when the omega is greater than omega n. So if you find the omega n, so I'm going to be somewhere here. When this ratio is negative. So if I find the omega n is going to be square root of 1200 divided by 0.388. You will get 50 25.59 radian per second. So omega, it's obvious that it's greater than omega. So as an engineer, you should avoid this case. We call this case resonance. So if omega is very close to omega, and we say that we have the resonance. So resonance, we want to avoid the resonance. It's a dangerous case for a mechanical system. So you should keep the frequency of the excitation force from the natural frequency of the generator. Alright, we continue on next Tuesday.
Sure.